he lets you do.
Today that this test was not a good test.
Honestly,
I was looking at it though, and I can see where they would not have gotten.
right.
It was pretty difficult.
In general, torque seems to be one of those issues for a lot of people.
It really shouldn't be that hard.
It's one of those things that it's very straightforward, but if you don't quite get it, it's one of those things that it just doesn't register for everyone.
Mm-hmm.
So, let me start with taking a picture of... Just kidding. I'll just read this out to you guys. Does that work for you?
That's fine.
Okay. So, we'll go to like very basics. We'll start there. So, a 25 Newton force, F, is applied to a bar that can pivot around its end with a bar radius of 0.75 meters. Sorry, I'm currently really frustrated with myself because I did not write down where I took this from. Oh, homework 17, number 4. Perfect.
Huh? What is it? Homework 17.
I can't tell if this is homework 17 of supplemental or expert TA. Because I did like 2 torque problems on the same paper and just let them...
I was going through the open stack questions and I know.
Okay. Usually I write down where I got my problems from, but apparently I was just going rogue. Okay, yeah.
Supplemental homework 17, number 4, is a gymnast weighs 450 newtons. So it is on supplemental?
It is expert TA.
Oh, expert TA.
Okay, so this is actually, apparently I just went through like really general basics, but...
Wait, what homework is it?
Go to homework 17, number 4. And we'll talk about like the equilibrium concept with it.
So you're just going to bring us back. Okay, there it is.
Yeah,
Bring us up.
yeah, that's my thought process.
So we're doing that one, number 4?
I'm going to give my laptop.
Okay, sounds good. Yeah, we're gonna do number 4. Okay, so sorry about that. I feel like a disaster today. Okay, so in the figure, the center of gravity of the pole held by the pole vaulter is 1.75 meters from the left hand. That's the value that I have. Right now, anyways, apparently it changed on me. And the hands are 0.69 meters apart. The mass of the pole is 5 kilograms. We're going to calculate the force in newtons exerted by his right hand and the force in newtons exerted by his left hand. But I'm going to change some of your values possibly. Okay, so keep mass of the bar at 5 kilograms. The distance between the hands of 0.695 meters. And the center of gravity held by the pole vaulter is 2.25 meters from the left hand.
2.5?
2.25. Just makes it easier since I already have the calculations. Okay. So, where would you start with this problem?
I mean, the forces are identified there already, so should we make a chart?
So,
Or choose the center of gravity? I mean, the torques.
so in this, don't look at your picture and start with your picture.
Okay.
I don't want you to like start with all of that imaging. No. I want you to draw a picture, draw your force body diagram.
I zoomed in and blocked out the photo. Except that we really can't know
Okay, so...
which hand does what.
Okay.
You know what I mean?
So that's a good point. I didn't think about that aspect. Okay, so he is gripping with his left hand under the bar, and the right hand is gripping above the bar. Touche, Lydia.
So when I did this, I just saw that both of his forearms are up, and I just made the natural assumption that they were both like this. I was like, that's weird. Why is his left hand doing more than his right hand? But now that I see his hands, that makes no sense. It looks like his forearms are both up, but I'm good now. I get it.
In the image, you can't see it well.
It's not very clearly described.
But picture it that way. So you've got to be able to put this pressure down or this force down from the right hand to be able to balance it out. This is a very rough bar.
All right. I drew mine so interesting.
Drawing doesn't have to be perfect, as you can see, as long as you just get a good idea of what's going on.
How did you know that that specifically was going to be the center of gravity? Is it always going to be the middle?
So the center of gravity, like when you determine it by center of gravity, it would be the middle, but it determines, like, different torque problems will tell you where your axis may be. So it really just kind of varies. The what?
The answer correct?
The overall answer?
Yeah. Is it
For
44.3?
For which one?
For the right hand.
For the right hand?
Or my
I have 158.6.
Okay, I'll think about it. Alright, got it. So it's 0.695 meters apart and 2.25 meters.
From left hand to the center of gravity? Yeah.
And the hands are 0.6 apart.
Okay. So, now what is your next thought process?
Okay, so we can set up. My first thought process was to find out how far the right hand was away from the center of gravity by adding the 2.25 to the 0.695, since it's that far apart.
Okay.
So you get.
Back up just a little bit.
Okay.
What do we know? What?
I was going to say, do we have to choose where this is a torque problem, right?
Mm-hmm.
Do we have to choose where to sum the torques?
So let's back up a little bit. What do you know about the net torque in this? You're kind of talking about summing the torques, but what do you know about the net torque with this?
That torque is going to be 0 because it's in equilibrium.
Right. So with that, we know that our clockwise and our counterclockwise torques are equal to each other. So, move this down a little bit. Okay. So with that, A is asking us to calculate the force in newtons exerted by his right hand. Starting off, what do you know about this equation?
Which one? Torque equals R times F?
Yes.
Or cross F?
Yes,
So
and
we're
then
trying to find the force.
right.
So we can theoretically do torque divided by R equals F, right?
Say that again.
Torque divided by the R equals F.
Yes.
If we kind of-
You can do it that way.
There's another way that. Well, force can also equal mass times gravity,
Right.
which we know the mass and we know gravity is like 0. So I guess that's how I originally did it. But
So you can set this up. I didn't initially set this up in a table, but for him, you'll definitely want to keep a table, or else that will screw you. He will take off points. I'm just not used to the tables themselves. So we'll start with a table of forces. Okay. So I'll just set it up like this for now. And then with this, you can pick your pivot where your left hand is.
So you can find the right one?
Because you have your distance from the left hand to the center of gravity, and then your distance from the left hand to the right hand, you can utilize that as your pivot point.
So you talk about where to equal 0?
Yeah,
Okay, that's because we're looking for the right one, so we just make the left one 0.
right.
Okay.
So what we're doing is problem 17, number 4 from Expert TA. Just because this is like a good torque problem. For some odd reason, when I was initially looking for this stuff, the supplemental homework wasn't like filing into my thing anymore, like my dashboard. And then now I just see like this whole chunk of supplemental homeworks located on the 25th of this month, but like they were not there. They were there before when I was doing stuff.
Yeah, they're in a chunk. They're not. Like,
Yeah, it's super weird. I don't understand. So that's what we're doing. This problem is, let me just kind of show you, mind my poor drawing skills. So we have a pole vaulter, and he's holding the pole vault. Center of gravity is right here. His left hand is 2.25 meters from the center of gravity, and he's holding it with his left hand, holding it from under the bar, whereas his right hand is holding from above the bar.
That one is this one.
And then the distance between the right and the left hands are 0.695 meters and mass of 5 kilograms of the pole. So that's where we're at. Had everyone draw their diagram.
You would just listed the forces.
And then draw their force body diagram. And then we're discussing the forces. 17, number 4. Okay, so as we were discussing, we can pick our pivot hand or our pivot location to be the left hand. So when we do that, what do we know for calculating the force of the right hand then?
We have to add the 2 to find the distance from the center of gravity? The distances? Or does that matter?
So go back to your net torque concept.
We need to add the sums of the forces from the left hand and the right hand.
Right, but we're looking more so, if the left hand is our pivot, we're looking to the right of the left hand and to the left of the left hand.
Oh, so we're separating those completely then.
Right.
Instead of adding them together.
So, what you're going to do here, what would you identify as the equation for calculating for your force of the right hand?
Wait, can you repeat that? Sorry, what?
What would you identify as, we'll just take the equation of the torque of the right hand. What would be that equation?
T divided by R. Is that what you're asking?
So, is what I'm saying is torque clockwise equals force of the right hand, R.
Yeah.
So, with this, what do we know as far as the torque to the left of the left hand? So, the counterclockwise torque. Just kidding, don't look at that area. Because we set up our forces here for our forces in general relating to our force body diagram, but now we're discussing the left hand as being our pivot point. So don't look at the table quite yet.
So when we're looking for the force that the right hand is exuding, our left hand is acting as the pivot point.
Correct.
So can you restate the question?
So what would be the torque equation to balance this out looking at the left side?
FR equals FL.
So let me go back to the diagram for you. So right here, we're considering as our pivot point. To make this easier, I mean, honestly, you can choose any pivot point, but this is going to negate a lot of your complications when you go to actually calculate. So if we considered this side to the right to balance out this side, what would we understand with that?
So the force of the left hand would be 0, right? If you're summing it around the left
Yes, force of the left hand is 0. And then we have force of the right hand times this radius being 0.695 meters. And then we have this area. What do we need to do with that?
So we don't add it at all? It's just...
So you're adding it, but right now you understand that your force of the left hand is 0. So what I'm trying to get you to understand is that if this is your pivot point, you're in equilibrium, then the force of the right hand times that radius is going to be equal to your force of gravity times that radius from the left hand, because you're looking at that being in equilibrium.
But then your right hand would be negative, right, since it's clockwise?
Correct. So,
I guess it wouldn't matter since
right, it doesn't really matter at that point, but yeah, you're correct. So,
I'm sorry, I'm still not fully getting it at all.
okay. So, I'm trying to think of a better way to explain this. Okay, I'm just going to continue to try and re-explain it, but we'll see. Okay, so we are summing our forces. We can choose any point to be our pivot point. Since we know the distances right here from either side of the force of the left hand, it's easiest when you do your calculations to choose that as your pivot point because you know from either side. So with that, if you choose this as your pivot point, the radius from the force being applied is 0. So your torque for the force of the left hand or your torque of, the left hand is 0. So you know that this current situation is in equilibrium. So if we weren't in equilibrium and the force of the right hand were greater, or the torque of the right hand were greater, then you would have a pole that's starting to rotate about the axis. And you know that if this area of the pole, if its torque were greater than that of the torque of the right hand, then it would also start to rotate about the axis. Thus, we know that our net torques, because of being in equilibrium, equals 0. So, if the force of the left hand, if this location of where it's applied is our pivot point, then we know that this side, when I rotate above this, does it show my little pointer? Mm-hmm. Okay. That this side is equal to this side. Does that make sense?
Yeah, because they have to equal each other out.
Right.
For it to not be, okay, yeah.
What do you mean by they're equal? Like in distance?
For the net torque?
For the torque.
Oh, okay.
We're not talking about equal forces. Okay. We're not talking about equal distances. We're talking about torque. So when we talk about net torque, the force times the radius of each side are equal to each other.
Okay.
So we have our force of the right hand times the radius from the right hand to the left hand. And we now know that that is equal to what?
The torque of the force of the left hand times the radius of the left. Right?
So the force of the left hand, this is the location where we chose our pivot point. So this is 0.
Yeah.
What about this? We still have this entire remainder of the bar. If I'm trying to think. Gotta be
That's
kidding me.
your force of gravity times your radius, right?
Yes. Yes. Is there a better way to explain this? I'm trying to think of like a way to explain it without me just giving you the answer. I know torque sucks. It really does.
I'm not seeing what you're seeing. I think that's my problem.
Okay. So basically is what I'm saying is since we chose the force of the left hand to be our pivot point, we know that this entire portion of our force of our right hand multiplied by this radius is actually going to be equal to the center of gravity, force of gravity, times this radius.
The radius between the left and the center of gravity?
Oh, yeah, okay.
So our torques have to be equal.
Yeah. Okay.
Okay.
I think I'm getting a little bit more.
So we can set this up as,
Force of gravity times the radius?
yes, and I'm going to set this as R1 and R2, just so you can signify. So as we calculate this, we're going to set up, we're solving for the force of our right hand. And we know that the first radius is 0.695 meters. And what do we know about force gravity?
Mass times
Mm-hmm. So we have negative 9.8 meters per second squared times 5.0 kilograms. It's going to run out of space. Okay. And that's multiplied by 2.25 meters.
Okay.
Scrunching a little. There we go.
Why is it also times 2.2?
Because that's the radius from the center of gravity to the left, to where like the force of the left hand is being applied.
So you just know with these problems that because it's an equilibrium that they're going to equal each other?
Yes, so that's the biggest thing to understand about equilibrium is that when you're in equilibrium, or for this case, your torque is 0. Your net torque is 0. That makes a big difference as far as understanding what's going on. Okay, so what do you calculate for the force of the right hand?
158.63.
Okay.
So that's all after you divide it over the other?
Yeah, so you would calculate this, the right side through, and then divide over your 0.695. And you take out the negative. Yeah. So that was A. Now B. B was to calculate the force in newtons exerted by the left hand.
Oh, so that's it for to find the right hand?
Yes, to find the force of the right hand.
And then you said these are the simple ones?
So the equilibrium ones I would consider a little bit more on the simple side just because you're able to negate some of those calculations. Yeah. So we'll go on to B. What do we understand about B then, or the force of the left hand in solving for that?
Would this just be the force of the right hand plus the force of gravity?
Yes.
So
We're
just
so
switching it
correct.
this time?
Yeah. So with that, writing down what Max said. Oh, oops.
And why is that?
So let me scroll back up to our.
So for the left hand, are we going to sum the torques at the force of the right hand this time?
Sorry, say that again.
So the sum, we're going to be putting the pivot point. Are we going to do it on the right hand or the center of gravity? It'd be the right hand this time since we're solving for the left.
So with this, it actually comes down to very simple some of the forces with this equilibrium aspect. Just because, oh, this is dark now because it's dying. So your force of the left hand is acting in the upward positive direction, whereas your force of the right hand and your force of gravity are acting in the downward negative direction. But then also, once again, your net torque equals 0. So we know that the torque of the right hand action, the torque of the left hand action, and the torque of the gravity of the bar.
This time you know the force of the left hand.
We know the force of the right hand.
Oh, sorry.
Or the torque of the right hand. So these all have to equal 0.
Okay.
So now with this, we can calculate by the sum of our forces. So this part is very simple at this point. So we have force of the left hand equals our 158.63 newtons.
So you don't need to necessarily use the pivot point to solve for it?
Nope.
Because you found-
In this case, no. In this case. Unfortunately, torque has many different cases, which makes it very difficult. That is why consistently torque seems to be one of the most difficult thing or like concepts for students to understand, just because there is no one single like rhyme or reason method of solving for it. So it takes a lot more critical thinking to be able to understand what's actually happening in the problem, and then really understanding the visual of it, which is the whole point of drawing your diagram to help you with that.
So if we're using the sum of the forces, I thought that the force left
Oops.
was going to be counterclockwise. So I'm wondering how the force left is positive after you moved it over?
So, give me just a second. There we go. And what did I do here? So, I don't know what I did that I wrote it down wrong. Okay. Give me just a sec. Okay. Sorry, it's not scrolling. Losing it. Okay. So with this, the force of the left hand is in the upward direction, and it's easier if I go back to the diagram to explain this. Okay. So your force of the left hand, we're talking about being still the pivot point at that point in time. So we had used that as our 0 initially. And then with this, our force of our right hand is in the downward direction, but it's going towards the, like if you were to pivot about that, with the pivot point being where the force of the left hand is applied, then you would pivot towards the clockwise direction. So we know that our force of our right hand is negative. Let me just note that there. And if you were to pivot about this pivot point with the force of gravity, you would pivot about it counterclockwise. So with that...
Wait, okay, I'm going to have to make you go back.
No, that's fine.
That's what I'm struggling with.
That's fine.
Finding the direction of the right hand. Can you explain that again?
Okay. Wes, do you want to show him?
Sure.
Okay.
So your fingers are the radius, so like looking at the force of the right hand.
So your index finger or your middle fingers?
Just doing these two, I guess. It's easier.
So
And
that's
then-
the direction of your radius, which is this way?
Yeah, and the bottom two is the force.
Yeah, the force applying to it.
So it's like down,
Mm-hmm.
and your thumb sticks out at you.
Okay.
And then it's like the opposite.
Because
Force
the
of
radius
gravity.
goes this way and the force is going up though, right?
Well, the force of gravity is going down. And then this is your radius.
So for the left hand, we're not even looking at the left, where the left hand is.
You're not
We're
needing to
looking
look where
at-
the left hand is right now.
So wait,
We're just looking at the center of gravity.
The force of gravity? Sorry, I'm getting really confused with that. I'm like, what?
I
So
know,
actually saying
it's
if
so
the
difficult.
Force of your left hand was the pivot point, so then the force of gravity would be turning like this, counterclockwise, or clockwise.
But I'm wondering
It would be-
why it's pointing this way if the radius is this way. That's what I'm saying.
Okay, so you have to understand that
I think that's confusing me the most, the directions.
Okay.
Is the-
So, in very general sense, before you look at the right hand rule, think about if this were greater, you would maneuver around this way.
Yeah.
Okay? Because this force is acting in a downward direction. So then,
But so is technically the force of the right hand.
no. Because if this were greater,
It'd be going the other way.
we consider this as our pivot point, so this would move around.
Yeah.
Oh, so like if we put pressure on that right hand, it would pop it up that way. So then,
Mhm.
okay. Oh, okay, that's easier for me to see.
Okay, yeah, that's
Okay.
all.
So biggest thing with that is really just taking a bunch of problems and sitting there and looking at, literally you just have to like do problems over and over looking at your right hand.
So we could,
It's the
like-
weirdest thing. It sucks. It just is what
So
it
we
is.
can look up torque problems and practice.
Yeah, so you can look up torque problems. Khan Academy goes through a lot of torque problems. It's one of those things that once it clicks, it just makes sense. Trying to explain it is very difficult sometimes just because people get very caught up in the wording rather than just like taking into account what's actually happening. So it's one of those things that you honestly just have to practice.
And did you use Khan Academy when you? Oh, okay. I'm gonna. Go
I
Khan
loved
Academy.
Dr. Yenin, but sometimes I had to teach myself.
Okay.
Yeah. So it's really, I mean, Khan Academy has a lot of great stuff. I know that there are other resources. I'm not sure what else is out there, but that's really the biggest thing is you kind of just have to get used to understanding that the concept of your thumb being the direction of the torque, the pointer finger being the direction of your arm, your radius, whatever you want to call it, and then your fingers like curling towards the direction of like where that force is. So you just kind of have to, I mean, you can do it like Wes and do two fingers. It doesn't really matter. Whatever, it's just the concept of like you have one pointer finger out and some curled fingers. So don't get caught up in like the very tedious aspects of it.
It's very simple.
It's a very simple concept, but you just have to kind of get used to using it.
For the force, on the center of gravity, we see the force of gravity. Is that what we're looking at?
As far as,
As for the force.
yeah, so that's our force there that's coming down. So
what's to say that we couldn't just go like this and bring our fingers down like that? Because that would still hit the force of gravity. And then it would be out. Does that make sense?
say that again.
Oh, I guess never mind. We can't use our left hand. I'm thinking.
Okay, I was like, what is happening? How is she? Yeah, no, don't use your left hand.
We reviewed chirality for OPEM today, and that you have to use your right and left hand. And I was like,
You scared me. I was like, how is that working?
okay, never mind. Okay, it makes sense. I got it.
Okay,
Move
so
on
yeah.
to the next
So
problem.
stick with your right hand. Okay. So,
I have a question.
yeah.
If your thumb is pointing towards you, that means it's counterclockwise.
If your thumb is pointing towards you,
Going
yes.
into the board, it's counterclockwise.
Right. So,
Or no, it's clockwise, right?
now I'm mixing it up. So, I never think of just like my thumb pointing in towards me. So, if you got your thumb pointing towards you, this is your radius going towards this direction, and your force is moving down, then you're going to rotate about this way towards your fingers. And now I'm like facing towards you guys. So yeah, it would be
Okay, I'm looking at it from.
right. I'm trying to like think about like the way that I'm showing you guys, but also the way that I'm looking at myself.
So is it counterclockwise when it's pointing towards you?
So if you're moving around, then yeah, counterclockwise.
Awesome.
Yeah.
Okay, now that we are all royally confused, let's move on.
It's fine. Yeah, that's honestly the biggest thing that I can express is just looking at problems over and over and over. And I mean, yeah. Khan Academy, like I said, will actually, like, since they'll actually walk you through it, sometimes with problems it's difficult because people will start to do it and they'll think, like, they'll start second guessing themselves. So while they're doing it right, they're starting to second guess themselves and then basically convince themselves that it's the other way. So I would maybe start with Khan Academy just because as they're going through a problem, you're starting to do it. Like, I would start the video, think about what's happening, pause it, so you can put down your diagram, put down your free body diagram, do the problem yourself, and do the right hand rule, and then play it through, because then they give you, like, that confirmation. Whereas if you're doing, like, book problems and whatnot, you don't always get that, like, immediate confirmation that you are doing it correctly.
True. Like, they'll tell you, pause the video and try it yourself or something like that, yeah.
Right. So that would be my biggest recommendation as you're trying to practice and getting this down, just to find a video that's going to go through a torque problem, get to where they give you what the problem is, pause it, do the problem all the way through yourself, and then continue watching the rest of the video and identifying things you did right, things you did wrong, where you need to improve. So. And okay, so I don't know if this is going to record anymore for us. Thank you. Yeah, of course. Have a good night. Good luck with studying. Hello. I got your email. Like, I saw it later today, so I didn't see the problem yet to do it.
Okay.
But I can do it later this evening for you and send you that, if that helps. Just because also my recording is going to die on me and I can feel it. Okay. So... Sorry, give me a second. For some odd reason, I did not also write this one down. I don't know why I just stopped writing stuff down where I found it. Okay.
I have a super random question.
Yeah.
So there's a problem on the exam from last year. It's our first synthesis one. And I'll just show you. But so I've worked through it. And most of it makes sense except for this one part. He divides this here by 4. Is it because my center of gravity is technically in force? Cutting that in force? Is that why? That's the only thing that makes logical sense, why he would divide that by 4.
Sorry, let me look at the problem first. Okay, so that's kind of the concept. The bigger thing to understand is that with this, it's talking about looking at it in like a mirror symmetry. So when you do the mirror symmetry,
Just
this
cut it down the middle.
is cut down the middle, and then it's looking at either side. So technically like cut in 4, but you have to understand that that's
Says
the mirror there.
And then the center of gravity cuts that half of the mirror in
Mm-hmm.
half. Okay, because there was another problem. He did that, and I was like, where did you get that number?
Yeah.
Okay, that makes sense. That's what I kind of figured after staring at it for 2 hours.
Okay, so we'll get through as much of this as we can while this is
That makes a little
still
more
recording.
sense. I'm glad. I was beyond confused with Tori.
Yeah, like I said, you just unfortunately have to do a lot of practice problems. So is what I was telling them, Andrew, where are you at with things? What's your kind of toughest subject right now?
Probably like the stuff we had just covered in class.
Okay. So I'll make a note of that. I'll probably do more stuff for you guys this evening just because I know that this is going to die on me. And then I'll do a recording. But we were talking about torque because torque is consistently one of those things that students struggle with. It's just one of those concepts that it's kind of straightforward once you understand it. It's just before you understand it, it seems like the most confusing thing ever. And so with that, what I recommend, like if you're, needing to focus on that area, if you pull up any sort of like Khan Academy videos or anything where they're going through problems, get to the point where they give you what the problem is, pause it, do the problem through, do, your right hand rule and everything. And honestly, this can apply to any sort of problem that you guys are working on. Do that and do it all the way through and then let the video continue through so that you can like get that confirmation of what you did right, what you did wrong, where you need to improve. Just because like book problems are really great. Do a lot of practicing on book problems. But the one thing is that if you're doing it and you're hitting roadblocks and you're not sure where, it's really hard to understand like what you're doing wrong exactly until you literally hit the final answer and you're like, oh, I guess that didn't match. So that's what I recommend in general as you guys are doing problems and kind of getting adjusted to different concepts and principles before you have it like down pat. Okay, so we have gosh, my drawings are really
Is this a different problem?
yes.
Is it on any of the required questions? My bad. Supplementing
No. As far as from what I remember, no. Okay, so with this one, what do you guys understand in general about this concept with Archimedes Principle? And what else? And pressure. More of Pascal's pressure in this one.
Pressure is the force over the area.
Okay.
Is this like those problems where it's like force 1 over area 1 equals force
It's like a
2
simple
area 2?
machine concept, yeah. Anything else?
Pressure of like the first thing has to equal the pressure of the second thing. Something like that.
Yeah, that's the biggest thing to understand with this. So the pressure of, like, we'll just label this as 1 and this is 2. The pressure of, like, the first pressure needs to equal the second pressure. Or as you do this, you'll start to understand that the, we'll just kind of go through it. Okay, so we have this setup. And we have, let's see, a force that is pushing down on the fluid that is right here. So we'll just draw that fluid. Okay, and we have across this, we have area 1. And we have, this will be force 1. And then we have our fluid over here. This will be area 2. And what do we understand if we're putting in a force on the left side? What do we understand is going to happen on the right side?
It's gonna, you're saying like one's gonna go down, one's gonna go up?
Yeah. So with that, if we're putting in a force, we're going to do something to the distance of the water level.
It's gonna decrease.
Right. And we're going to do something to the distance of the water level on the second side. And you're going to have an output force.
Oh, they're dying. And we're gonna have an output force, you said?
Yes.
Okay.
So we have an input or a pressure 1 of 10. Sorry, for some odd reason I cannot find where I found this, so I'm like trying to go off of the jumble of my notes. And then we have area 1 is equal to 2
Is that
meters
K?
squared. What?
Pascals?
Yeah.
10 pascals, is that what you're?
Yep. 10 pascals for the first side or the left side. And then area 2 is equal to 4 meters squared. And okay, so as we go through this, we are looking for what? What things do we have and what things do we need?
We have the pressure of 1 and we have the area of 1 and, oh, we're missing the force of,
We're missing the force of the second.
yeah.
Okay.
So, yeah,
So we know that we need to solve for our force 1, our force 2, and from that we can also solve for obviously our pressure 2. And by the end of it, we want to solve for our mechanical advantage as well.
So force 1, force 2, what is that third?
That's pressure 2. I mean, you don't necessarily need to solve for pressure 2 on this, but it's a very simple equation, just to kind of remind you, and then we'll look at our mechanical advantage. Okay, so once it loads, maybe. How would you start by solving for your force 1?
So
He gives us the
pressure
equations,
equals
right?
force divided by area. So
Yes.
we can do pressure times the area equals our force. So our force equals our pressure.
What'd you say?
Oh, no, I just said he's gonna give us the equations for Archimedes, right?
Whatever he has on your guys' exam stuff. Usually under each of the exams, I think he puts the equations that you'll have, and it's like on that main overall equation sheet. Otherwise, I don't know.
Do we know the pressures?
So we know the pressure of the first
Okay,
side.
so we can find force. I just didn't see which one.
Yeah. Sorry, I hate when it like flips back and forth from the first and the second page.
So we pretty much take it into sections first, like solve for this first and then solve for that.
Mm-hmm. So with this, we can solve for our force 1. I'll try to just keep it on this page and it'll make it a little bit easier. And what would you have from that?
What's our pressure? Is that
It's 10 pascals. Sorry, my drawing
so
over here.
10 times the area, which is 2 meters squared, so 20.
Okay.
Our force 1 would be 20. And since we know that force 1 has to equal force 2, we know that our force 2 then is also 20? Or is
No,
that
it's
wrong?
our pressures.
Or our pressures are the same.
Yes.
So, because pressure 1 is the same as pressure 2, right? So
Mhm.
pressure 2 is
Then
10.
you use that.
So then you can solve it for force 2. It would be
So pressure 2 would also
10
be
times
10?
Yes. The biggest thing to understand with the simple machine is that your pressures are equivalent. You may have different area and different input or output force, but your pressures remain the same.
Okay.
Yeah, they're in the same machine.
So what would force 2 be?
40.
Okay.
So then you want to find out what the mechanical advantage of it is.
Mm-hmm.
So don't you just divide force 1 divided by force 2?
Vice versa. Because what we're looking at is we're inputting into this machine 20 newtons. And through the simple machine, we're getting an output of 40 newtons.
So it'd be 20 divided by 40, or 0.5. Or sorry, otherwise 40 divided by 20.
Yeah, 40 divided by 20.
Or mechanical advantage is 20.
So you just literally divide them?
Mm-hmm.
Okay.
The biggest thing to understand with that, the point of your mechanical advantage is understanding what your simple machine is doing for you. So I'll explain that again. You're putting in 20 newtons of force, and through this machine, it's giving you an output of 40 newtons.
Okay.
So with that,
This is showing you that's giving you double?
yeah.
Oh, okay.
So your mechanical advantage is 2
Oh, okay.
because you're doubling your force.
Okay.
So to be able to formally calculate that, it's the 40 newtons over 20 newtons. But that shows you that you're doubling that mechanical advantage.
What is Q when relating to fluids? Is Q flow rate?
All I'm thinking about is Q from temperature stuff, because that's what we talked about with lab today. So let me see your equations.
But is the Q, or is it even a Q? It's probably really not a Q. Equals the area times the velocity.
So this is an example of Archimedes' principle here?
What's that? There.
That is a Q. That looks like the same Q from the temperature flow.
So probably flow rate, huh? I haven't studied that portion.
Honestly, I don't remember. It's not coming back to me.
Okay, I'll look it up.
Yeah, I don't have it physically written down, so I don't remember at this point in time.
This is an example of Archimedes' principle here?
So this is more of your pressure. We're going to do an Archimedes Principle one next.
Okay. Yay!
Yes.
Archimedes is referencing the weight of, when we put an object in the water, amount of water
Has more to do with
Mhm.
density stuff?
Yep, so that's density stuff. Think about Archimedes is what you were evaluating in lab. Yeah.
This is so much better than torque.
I have a question that has nothing to do with what we're talking
No,
about.
I'm just kidding.
How do you change RPMs to
to
radians?
2 pi conversion. I can't remember if it's 1 revolution for every 2 pi.
One revolution is 2 pi.
So then you have to divide it by 1 minute divided by 60 seconds, or 60 seconds divided by 1. You have to do all the whole stoichiometry crap when you get into it. I think of GChem.
Yeah. I always do stoichiometry. even in like nursing med calculations, they would teach us like a different way. Yeah, they would teach us a different way first semester, like desired over have, and it just never made sense. And I was like, why is anyone doing anything but stoichiometry? So, love stoichiometry.
Yeah.
Get real used to it.
Okay, so you take the RPM, you times that by 2 pi, and then you divide it by 60 seconds. And then that should give you your radians per second squared.
Thank you.
Yeah, no problem.
What was the formula again?
So you take your RPM, you times it by 2 pi radians, and then you divide it by 60 seconds.
You guys have that on this exam?
Yes.
Well, there's a question I was looking at that has to do with when you're talking about
Yeah, I had to look it up.
angular velocity.
Oh, okay.
They gave me the angular velocity in RPMs.
Mm-hmm.
So, yeah.
And there's a couple kinetic energy of rotational kinetic energy.
Okay.
I don't know if he said that today in his
That feels like so long ago that...
Wait, what did he say?
I don't know if he said it or not in his review, but you do need to know like the angular acceleration, and that's in radians per second squared. So if you give it
Right.
RPMs, then you have to change it over.
Yeah, that stuff feels like forever ago that I genuinely didn't think that was on this exam.
Did he also say we didn't have to know flow rate? Is that something we didn't have to know?
So that's something I thought he said during, when was it? The last class period we had. I thought he said we didn't need to know that. But then he confirmed today that it was the, what is it called?
Is it the one that uses like N? Or like a N, like some kind of letter that looks like N for like viscosity?
We don't need to know
coefficient?
Pascal's law or whatever that is.
Yeah.
But we do need to know flow rate. I swore he said we didn't need to know that, but he covered it in his review today. So, yay.
What is the, you said Poiseuille's law or something like that?
Yeah, was
What is
there you
that?
go. Don't know.
We don't even go for this test.
Haven't gotten there.
That has to do more with like friction.
I missed what
loss
you
of
said,
friction
so.
to whatever it was.
So I thought we didn't need to know chapter 12 at all, but.
What's chapter 12?
Do.
That's about flow rate
Flow
and stuff.
rates.
I know that you need to know
Bernoulli's.
Bernoulli's. Yeah, you'll need to know that. You'll need to know that. You'll need to know static
Laminar.
and dynamic fluids.
Yeah, like laminar flow and whatever the other one is. Are you confused on flow rate, Andrew?
Not really. I just didn't know what we didn't need to know because I don't want to learn what I don't need to know.
That is fair.
Isn't that such a sad concept?
Yeah, I need to know.
That's like, this is gonna sound really horrible, like that we just don't care to learn anything beyond what we just need to know for this test.
No, I mean, that's pretty common. Yeah, that's not an awful thing.
So flow rate should be pretty simple, right? It's just, oh, that's what the Q
That's
is.
what the Q is, yeah.
Oh, yeah.
Because it's your area
Yeah.
by your, yeah.
And what's the equation for flow
Yeah, as you guys were talking about that, that's what I was sitting here thinking about, and I was like, well, when they're done talking.
I'll jump in and say that's something too.
And
Okay.
what's the equation for flow rate?
Area,
Times velocity.
yeah.
Average velocity.
Is it velocity? I don't know.
And it's the velocity of, like, the volume. So, like, it's your volumetric flow rate is
Yeah,
what
you
Q
can also
is.
do the volume over time.
Yeah.
True.
There's some equations in here that maybe I'm just blind as a bat, but I can't ever find them, so. I think it's because you're supposed to be able to derive to it.
Yes, so that is something that actually he and I talked about when we met today, that he said that from your equations, if you just start out with like just the derived equation and you don't give like the actual initial equation showing how you derived it, he will, yeah, that's just a math calculation at that point and he won't count that. So as you're showing your work, take that into account.
That's so.
I understand it to an extent, but even sometimes in the textbook it gives us already derived equations.
I do agree with that,
Yeah.
which is
Like
unfortunate.
Q divided by VT, like that
But all
Like,
the
very
equations
first
given
thing.
to us on like the equation sheet, those are fine to put, right?
Those should be fair game.
Okay.
Yeah. So utilize those and then derive from there.
Wait, so was Bernoulli's the one that he wanted us to derive from the
No,
something?
that one he gives you, it's the P1 plus 1/2 density V squared plus density
There was,
GY,
there was one where he,
something like that.
there was
Yeah.
one he did in class where DJ
I don't know the
asked
exact
if we
equation,
needed- that he told us we needed to derive from the sum of the forces is equal to mass times acceleration. I don't remember which one that one was.
That's the inertia one, the torque, inertia times angular acceleration. I need to.
Okay. Something else concept-wise to understand
Bernoulli's.
before we jump into Archimedes Principle. What do you guys know about fluids?
Like how they flow.
Like, what are they made up of?
The solid, liquid, gas, is that the kind of stuff you're talking about?
Yes, that's the stuff that I'm
Fluids
talking
are
about.
Made up of
But
air.
mostly, we know, at least in this class, you're going to use the fluids in terms of gas and liquid.
Yes,
Yeah.
that's what I'm looking for.
Liquids hold
Sometimes it's easy for students to get caught up on what they consider everyday fluids, and they think of just a liquid. And so taking into account that that's a gas as well. I wouldn't be surprised if that's a concept question.
Archimedes.
Yep.
Archimedes. Do you have a problem with that?
Yes. Okay, so bless you. Yeah, there's nothing more to talk content minus on that.
Do you guys look at any of the Old Testament study?
I usually do.
You do? I always start with last year's test because that gives me a good basis of
Well,
what.
all the other tests are so much different.
Yeah.
Does it help?
I think it does for the multiple choice.
Oh, because that's true, he's most likely to use
Some of
that.
them like give me an idea of what we're going to be on, but
There's a lot of problems in the ones that he gave, which is a good thing to look at, in my opinion, if you're not quite solid on it. Last year's test for the synthesis, those were difficult.
Okay, so what I have is an object is 10 newtons when measured outside or in the air. And then it's measured at 2 newtons when in water.
As 2 newtons?
2 newtons. Yep. What can you tell me about the force buoyancy and the, we'll start with that.
The
What was the
buoyancy is
first one?
just
yeah, can you say it again?
I'm sorry.
Okay.
How many newtons?
So I have an object is 10 newtons when measured in the air. And 2 newtons when measured in water.
Is the buoyancy just the 10 newtons minus the 2 newtons?
Yes. So what do you understand about that?
That the buoyancy is equal to the weight of the object that's in the fluid space? I don't know how to word
It's
it.
Isn't it like the density of the fluid times the volume displaced times gravity? That gives you
Yes.
your force buoyant?
That's that equation where, this force point.
Okay. So we have that equation. Plus, we know that with our force buoyancy, theoretically, it should equal the weight of the water displaced. So we would assume that to be 8 newtons. But then we want to calculate for the efficiency as if we were doing it kind of like what we did in lab. So then using that force buoyant equation, the volume of the water multiplied by the density by gravity, calculate what your more accurate force buoyant for.
So it's just
whatever that would be.
Density times gravity times the volume of what?
The volume of the water. So basically is what I want you to understand is looking at what the force buoyant should be just by looking at the weight of the water displaced and then looking at what it more precisely calculates to be and then looking at your efficiency.
So is the more precise way using that equation?
Mm-hmm.
Okay. And the less precise way is just seeing what?
Just the sum of the forces.
So do
Which
we,
equation was that?
So we're looking at Archimedes Principle. It's the force buoyant equation. And then I also want you guys to draw force body diagrams because we did not start with that right away.
that's true. What is it? Okay.
Oh, yeah.
So
just
you
drawing it, what would be better, drawing it in the air or once it's in the water? Or both?
drawing
Both.
both, but
Okay.
draw both. But when we're looking at the sum of the forces, we're looking at the object being in the water.
I have to leave.
Okay, sounds good. Good luck with studying. If you have any other specific questions, if you can send me those as soon as possible. Tonight I'm gonna do supplemental homework 17 number 4 because Andrew had requested that, and so I'll do a recording from home of that. Not sure how late it'll be, unfortunately, but hopefully you guys can see that before you go into stuff tomorrow. But if you think of anything else, I can do it this evening on my own time and work myself through the problem and then try to be able to explain that via the recording.
Okay.
Oh, thank you.
Sounds
Yeah.
good. Thank you.
Yeah, good luck.
Thanks.
Unfortunately, this is one of the tougher ones, so just go in with a strong mentality.
Yeah.
Ooh, that's a good one, 17.4, because I was looking at that one earlier, and that one I was like,
Yeah. So I'll
there's
go
a
through that one.
question, Number 2, it's this horse one, where it's leaning up against a wall. Do you think that's going to be something he would ask?
What is it?
So it says calculate the magnitude and direction of the force on each foot of the horse in the figure. So it's this horse is sleeping on the edge of a wall, it's leaning up against a wall.
Maybe.
But it's calculating the magnitude and the direction of the force. And so once
You could have a problem like that where you've got the horse, but it's going to ask you more about. I don't know on that one. Just because it's only asking you magnitude and direction of the force, he's going to have, I would assume, more tough things on there. But I'm picturing I don't know. I don't even know what I'm picturing.
So when I was doing it, I was trying to work on that one before I went to supplemental homework, and
Mhm.
I looked it up on the internet to see how they did it, and it looked really, really difficult.
Really?
Yeah, it looked like something that because it's got this horse and it's like sideways, but then it's leaning up against this wall, so you have the force of the wall, and then you have it's just
A lot going on.
there's a lot going on, and then
If you send me the like supplemental homework number and like problem, I'll include that one.
I don't think it'd be necessary to even include it though. It seems really dumb.
I mean, if it makes you like nervous enough, then I can work through it and like do it in the recording this evening.
Do you want to see email?
Yeah, that way I can like have a spot to look at.
Okay, what's next? Are we still
Okay,
doing that?
so yeah. So what does your force body diagram look like?
You got the force of gravity.
Or which one, the air or the water one?
I guess both.
So in the water one, we're gonna have force of gravity, but then counteracting it, we're gonna have force buoyancy.
That's what I have to do.
So really with the rest of that problem, it would just be calculating your efficiency from what you actually calculated through the force buoyant equals volume of the water times the density times gravity equation versus the just 8 newtons that we had assumed.
Okay, so the density would just be the one of water, right?
Yeah.
How do we figure out how much volume it is? Is that what we have to divide out the gravity out of the newtons?
So the way that you would want to set that up is you would want to break up your units for the newtons just so you can cancel things out. So it would be 8 kilograms times meters per second squared, and then that's over the density of water. I'm not sure if he has that on your equation sheet or if you just need to know that, but that's something I would get to know. So that's 1,000 kilograms per meters cubed. And then you'd multiply that by 9.8 meters per second squared.
Wait, so for the volume, we still put the newtons?
What?
No, I'm wondering, like, if it's, how are we supposed to be solving this? That's pretty much my question, because I'm just,
Okay, so basically you're looking at your newtons over your density of your water times gravity, and that'll give you, from that equation,
wait,
your,
so it's divided by the 1,000?
yes.
Why?
Okay, so basically in general, just look at your force buoyant, knowing that that's the weight of the displaced water, and then calculate it through with the actual force buoyant equation. I wouldn't be surprised if he has you do some sort of equation where you need to look at what you assume from the weight of the displaced water versus what you actually calculate for your force buoyant.
So, I'm sorry, I'm still, like, confused about how to do this.
So we discussed that 10 newtons in air is the weight of the object, and then 2 newtons in water being the weight of the object. So we assume that our force buoyant is 8 newtons because we assume that that's the weight of the displaced water.
Oh, so wait, so we're just gonna have the force, the newtons, and then it's divided by 1,000 times the 9.80?
So then you would set up your force buoyant in your equation
Yeah.
and try to solve for it.
Like the volume.
So utilize your force buoyant equation to try and solve for force buoyant.
So force buoyant is equal to that, the volume of the water times density times gravity.
Right.
So I just assumed that the force buoyant is the 10 newtons, or the 8 newtons.
So we would assume the 8 newtons.
And then it's just divided by the density and the gravity.
Mm-hmm. And that would give us the volume of the water.
Oh, okay.
So it's all before, okay, it's all for volume.
Yeah, that's what I was
Right.
thinking. Go ahead.
So the thing is when you do that, you want to basically, in general, I'm not sure how his Archimedes Principle equations are going to be, but I wouldn't be surprised if he has you go through and looking at the assumed force buoyant and calculating for what would be appropriately the force buoyant, and then having to look at your, error or anything.
Okay, I got.
Okay.
I know you just said it, but I'm still confused.
You're killing me. I'm just kidding. Okay, so with this equation for the force buoyant, we're solving for the volume of the water because apparently we did not know that. So if I told you that the volume of the water were 8.2 times 10 to the negative 4th meters cubed, solve for your force buoyant at that point.
The 8 times whatever.
Yeah.
What was that again? That's the volume
8.2
displaced.
times 10 to the negative 4th meters cubed. Or,
So
yeah.
volume displaced.
That's the volume of the water
Before
that's
the
displaced.
100. Oh, that's
Wait,
Yeah.
so you said what the volume was before?
Sorry, it got so confusing because I didn't write down every bit of my notes. We're going to scratch this entire problem.
Okay, I was gonna.
In general, force buoyant, what do you know about that?
It's like the force that comes out that battles the gravity.
Yes. So we're looking at the weight of the displaced water being our force buoyant. And then with that, we also know that our force buoyant equation is what?
It's the density times volume displaced times, I can't remember the
Times gravity.
Okay.
Okay, so those are the biggest things to understand about your buoyant force.
So you literally can just solve for that. So like if you were wanting to find out the volume displaced, you can, if you know at least your force buoyancy and your gravity.
Right, you can solve for your volume displaced if you're not given that, or if you're given what your volume displaced is, what your density, you should know your density of water, or unless you're given some other sort of fluid, you'll probably be told that, but if you're just told water, you should probably know that.
So if we're given the volume, you just solve the equation as it is?
If you're given the volume, you know the density, you know gravity, you could solve for force buoyant to then be able to, you can manipulate this to go backwards, is what I kind of wanted to get you to understand, but I don't think I gave you all the pieces. I might have made it super confusing.
Go back and do that as like some of your forces.
Yes. So say you were given your volume of water and your force, given your volume of water displaced and the weight of the object in water. I'll just give you a simple thing. Say your volume displaced is 3,000 meters cubed. And solve for your force buoyant.
Oh, so it'd just be 3,000 times gravity times 1,000.
Mm-hmm.
Okay.
Do that, and then since I don't know what that value is going to look like, I want to make sure I give you a value big enough for another
I'm
one.
not actually going to solve
Well, thanks. Let me calculate this through. Basically, I want you guys to understand that you can utilize these pieces to manipulate to move wherever you need to.
So this relates to Archimedes Principle, though, right? Like it's not.
This is,
Archimedes?
yeah, your force buoyant.
Wow, torque is so much harder than this stuff. Oh my gosh. Sorry, I'm like really late to work, so.
No, you're good.
Thank you so much.
Of course.
I have a good day.
Okay. In general, I want you to understand that if you're given your volume of water, you know your density, and you know gravity. You can from there calculate your force buoyant. And if you are given what your weight of the object is in water, you can utilize your force buoyant, add it to that weight, and be able to identify what your object actually weighs, like in air. I can repeat that again if I need to. Okay. Okay, so look at your force buoyant equation. If you are given the volume of water, you know the density of water, you know gravity.
You know gravity, so you can solve for force buoyant.
You can solve for force buoyant. So if you're given volume of water and what the object weighs when it's in water, you can identify what your object actually weighs in the air.
By doing, just adding them,
Mm-hmm.
because it would, the object in
Because
the
you're-
water, that's just the weight of it in the water, well, I guess.
So it would be your force buoyant plus your object in water, because your force buoyant is the difference of those, of the object in water, object in air.
So if we have
Okay.
the, like.
I made
the
this
problem
so
we did,
confusing
we
and I'm
did the-
so sorry.
We did the 2 newtons in the water.
Uh-huh.
Literally, if we had the force buoyant, let's say it was 8, then we can say, okay, it was 10 newtons. Is what
Right. So if you're given volume of water and then weight in the water, you can be able to maneuver that equation backwards to find the object in air. A lot of times I think that it's easy to get so used to the problems that you're doing that you're so used to getting, the object's weight in air, object's weight in water, and moving that way in the equation that you kind of forget that you do know all of these different pieces to be able to calculate wherever you need to get.
Okay, so.
Sorry.
Here's another thing
I
to
feel so
clarify.
bad.
The weight of the object in relation to the force buoyant. How does that relate?
So your force buoyant is the difference of the object's weight in air and the object's weight in water.
Okay.
And the reason being is because your force buoyant is determined as the weight of the water that is displaced by the object.